I'm really glad that the joint colloquium gets back to SISSA. Hopefully, for next year we'll have also the main auditorium of the patrons. But also, all, I'm glad that we have Alice and Guionnet with us today. Thank you very much for the keynote. Since this is a joint colloquium, I'd like to invite Andrea to say a few words.
Thank you, Andrea. Thank you all. And I would like, just on behalf of our director, Hadish Abokar, to welcome our distinguished lecturer and to thank our colleagues at SISSA for this joint activity, for hosting this joint activity. And thanks to the speaker, it's a topic that is very dear to many ICTP research lines. And in fact, actually, today's speaker has been also a director in a very decent ICTP school. So, I mean, it's a topic which touches almost many of the things we do, statistical mechanics, machine learning, PDEs, and dynamical systems. And so, I mean, it's definitely very exciting for us to listen to this beautiful event. And thanks to everybody and to SISSA for this organization. Thank you very much.
Thank you, Dario. And now, Tamara will do the speaker.
So, welcome everybody. So, it's a pleasure to have Alice with us today. So, Alice is our leader of analyst. She has a lot of spectacular results in the theory of Bernoulli Matrices, large deviation, probability, combinatorics. And for her achievement, she has been recognized with numerous prizes, among which the Rollo Davidson Prize, the Loève Prize, the Blaise Pascal Medal, and many others. And she was elected to the French Academy of Science and foreign member of the National Honorary of Science of the US. So it's a pleasure to have her here with us today. So she's speaking about mathematicians.
Okay. Anyway, it's a very good to because I can, maybe I can remove it. Okay. Maybe it's okay. Now it's better. Okay, so thank you very much for the kind introduction. I would like to take this opportunity to thank SISSA and ICTP for the invitation. So the first time I came here in 2018 was actually to start a partnership between Montgomery of Lyon and SISSA, and I think it's going well. I was just asked if I was working with someone here. I'm not, but it's getting close because one of my former PhD students, actually my PhD students, and one of the former PhD students of Tamar are working together. And Jean Barbier is working with one of my postdocs, so you see that somehow the links are getting closer and closer. And then I had the pleasure to organize with Tamar and with Etov this very nice community which was taking place at ITTP. It was a great event. So thank you for all that. And I hope that the links between SISSA, ICTP, and Lyon will continue to flourish. Is it okay? Okay, great. So let me tell you a bit about large Wigner matrices. And what I would like to show you first is actually that indeed it's a topic which has many applications in many fields, and in particular, which is motivated by many different types of questions. Do you think that we should shut down the lights? Maybe I don't do anything. Yeah, so yes, so what I would like to do is first telling you a bit about all the motivations. And yes, there is kind of an egg to my movement. Okay, and so we first start to explain you about the motivations of studying large Wigner matrices from physics or statistics. And then in the second part of the talk, I want to tell you about what is the research about Wigner matrices these days, what are kind of the hot topics, nice questions, which were studied on the open questions. So you get a third kind of flavor of motivations, and then go on the kind of math result that we all after. Okay, and so the field from the matrices it's quite recent. It was born only 100 years ago in the work, actually a bit less, in the work of Wishart. And so Wishart was considering a big array of data. So I like to take this picture from matrix because it looks to you like this. And he was wondering how he could, if he was thinking that the data as noise, how could we recover the information from the observation of the noise? Okay. So a simple example is, imagine you are given a matrix S, which is a signal, and you add some noise with some intensity, which is here denoted theta. So when, if you just observe one, can you recover and eventually estimate the signal S? And of course, the idea is that if theta is 0, you can recover directly the signal. And so if it's small enough, you can eventually recover that, the signal. But if the noise is too big, of course, at some point, you won't be able to recover the signal. Or maybe you can in a good sense. So this is where some of math are useful to try to understand when this recovery is possible or whether you can build algorithm to do so. So of course, Wishart was not going maybe as far in his questioning, but it was really his first question why he wanted to study random matrices. It was to study just the matrix with only noise, to understand, for instance, how the spectrum of a matrix with only noise was going to behave, and to compare it with eventually the spectrum of the matrix that was just observing. Okay. So that was kind of the beginning of the story of random matrices, and it's actually nowadays a question which is very very standard and very actual, in particular with big data. So we want the dimension of the matrix to go to infinity. Okay. So because yes, what will interest us also later, so it's not only when the matrix is random, but also the size of the matrix goes to infinity. This is a large matrix. Okay, so the second place where random matrices appeared was in the work of Wigner, so the physicist. And Wigner had the idea to approximate the Hamiltonian of heavy nucleus by a large random matrix. So the idea that the energy level of the Hamiltonian would be approximated by the eigenvalues of a random matrix, and this random matrix will be chosen as random as possible within the physical constraints which will be known to be satisfied by the system. And it turned out that somehow when he plotted this energy level, it looked kind of similar to the plot of the eigenvalues of large random matrices. And anyway, what he said is that if it's not close enough, then maybe it's that you forgot some physical properties of the system, and you should just make a more complicated maybe guess about the large random matrix. So that was kind of an interesting coincidence, and there was one which was even more surprising, at least for mathematician, which was due to Montgomery, so about 20 years later. And what Montgomery conjecture was that, so if you look at the zeros of the zeta Riemann function, so it has trivial zeros on the real axis, but one of the big conjecture in mathematics is that all the non-trivial zeros lie on the vertical axis, and that what Montgomery conjecture is that they all lie on this. Well, if you look at the zeros on this vertical axis, then if you look at it far away from the real axis, the distribution of the zeros should be close to the eigenvalues of a random matrix. And again, there was a lot of numerical terms, which shows that somehow, I mean, if you look at this looks quite the same. At least it's very different from what you would get if you would just draw points at random, like a Poisson process. So, in fact, what is interesting is that this conjecture of Montgomery is still wide open in mathematics. And for a long time, it was a source of new conjecture on the zeros of Riemann Zeta function. But what is interesting is that nowadays, there are really theorem of the zeros of the Riemann Zeta function, which have been proved by using this relation. And the idea mainly was that the question which could be solved at the level of random matrices, because somehow they are a bit simpler, that they are complicated, but still simpler than Riemann Zeta function. And then using all this theory from random matrices, would be seen that many ideas could be used for the zeros of Riemann Zeta function. So this, all this history showed that there are a lot of interest in understanding the universality of the spectrum of large random matrices. So if you change the model of a random matrix, how will you change the spectrum and so on? And how, for instance, the spacing of the eigenvalues are distributed. So if you think about, for instance, the Hamiltonian of every nucleus, in particular interested in the difference between two neighborhood, two energy levels. Okay. Then there was another very intriguing relation which goes in another direction, which is 3D quantum gravity. And this relation was made by Bloch and the Blaise Pascal algebra. And what they showed is that if you look at the trace of moments of random matrices, they can be seen, if you compute the expectation of the trace of a random matrix to some power, you can see that it will develop in terms of the one over the inverse of the dimension, and the terms, the coefficient, will count graphs. And they will count very interesting graphs, because they will count graphs which are sorted by the genus of the surface on which you can embed them. And this was used quite a lot in the 90s to actually enumerate a complicated graph, because in some sense, it was easier to calculate integrals over matrices than enumerating these graphs. Okay, so that was another, so we are now in the end of the 70s. Now there is a connection in mathematics, which was made also with another topic, which was basically operator algebra. So that's kind of much more theoretical. And the point was made by Voiculescu. And Voiculescu was working in operator algebra, asking himself about properties of free groups. And to try to answer this question, he established a new probability theory, but where the variables, random variables, are non-commuting. Okay, so that could be a general probability theory, but what he did was to add this notion of freeness. So if you think about probability, what is probability if you compare it to, integration? If you're a student, what is the difference between probability and theory of integration? For me, it's mainly the notion of independence. Many results in probability theory are built on the notion of independence. We're always trying to go back to this notion of independence. So what Voiculescu did was to propose another notion for this non-commutative variable, which is the notion of freeness. And what was nice was that this notion of freeness is related with the notion of freeness in groups. So what is a free group? It's represented here if you have two generators. A free group, it's a group when you multiply by an element, you will never come back to the neutral element. Okay. So here this means that if I have B and then I multiply by A and by B minus 1 and so on and so forth, I have this KD tree because I will never come back to the neutral element. And so the notion of freeness that Voiculescu defined has this property somehow that you are of freeness in groups. And what is now the relation with random matrices? So what Voiculescu found out is that if you take two random matrices which are independent, and with size going to infinity, at the limit when the size is infinite, then these variables are free, in the sense of free probability. So this means somehow that random matrices are as independent as you can imagine. In fact, their eigenvectors are very independent. So they're really non-commutative objects. And so the point nowadays with this theory is that, of course, it's very, very useful in operator algebra, but it's also very useful for the theory of random matrices, because it became the natural framework in which we can study random matrices with size which are infinite. So you can do many computations by using tools which have been developed in this setting. For instance, if you have two random matrices, A and B, and you want to compute the spectrum of the sum, A plus B, then free probability will tell you how to do that. It's called free convolution. Similarly, if you want to multiply them, free probability will give you formulas. And nowadays, it's very much, these formulas are used quite a lot, in particular in very applied sciences like finance. And I listened to a talk by Jean-Philippe Bouchot, where he was really using that in finance. I mean, he had a hedge fund, and he needs to understand how the assets are evolving and comparing different scenarios, and he's using free convolution quite a lot. Okay, so this is another, so this is nice because all these slides are kind of independent, so it's like all the beauty of random matrices. So this is another nice relation of random matrices, that they are a stereotype of strongly interacting variable. So what is that? So it's a losange, and you want to tile your losange with hexagons. It's an hexagon, and you want to tile your hexagon with lozenges, which are in three directions. You have the green and dark blue and light blue, depending on the direction. And you can check that this is doable. But this will not be doable for all domains, but for this domain, it's possible. And in fact, you have many possibilities. And now you ask yourself, well, what do I see if I'm given this tiling at random from all my possibilities? And so this is quite complicated because the distribution of the tiling is not very easy to compute. But what was noticed is that if you look at the tiles, for instance, the green tiles on a vertical axis, you can construct this distribution because somehow you can count the number of configurations with the same boundary condition on the left and on the right. And in fact, the distribution of these green tiles is very similar to the distribution of the eigenvalues of random matrices. So what happened was that a lot of things which were understood in random matrix theory could be used to understand this kind of question of what is, for instance, the limit shape of a random tile. There are actually other, maybe more mysterious relation of random matrices with a particle system, for instance, with integrable models, and the Toda chain. So I didn't write it because it's not as picturesque as this one. But you can see that random matrices can be used also to understand Toda models. And this was done actually by Tamara Guido and my student Rollo. So this is yet another nice connection of random matrices, and this is with the evolution of stochastic interfaces. Okay, so what is the relation with a stochastic interface? So you can what was shown experimentally, but first it was kind of understood theoretically, is that if you look at certain random interface, they will fluctuate as the largest eigenvalue of a random matrix. Okay, and how can you see that? So you can, for instance, consider the constraint dynamics with the totally asymmetric simple exclusion process. So this is a simple process where you have particles on a line, okay, and each particle will have a clock which ring at exponential times to the right, except if there is a particle just before, then it will just not do anything. Okay, and so this is kind of known as a model for a traffic jam, because you can imagine that these are cars which, you know, in a traffic jam, and from time to time they advance by one position, but they're not going to jump one over the other. And the relation, so with the random interface, is that you can think about this as the evolution of some interface by just saying that when you do a jump on the right, so this means that you have one, the flux have gone by one, and you just exchange this triangle by an up triangle. Okay, so this, you can see that there is a one-to-one bijection between the moves of this interface and the move of the tether. And so what was shown is that the evolution of this dynamics is again related with the evolution of the eigenvalues of large random matrices. In particular, if you start with, for instance, particles which are just all before zero, there is a particle everywhere and just zero on the right, then the first particle will move exactly asymptotically like the largest eigenvalue of a random matrix. Okay, and in fact, so what was shown by Takashi and Sano is that if you have experiments of the interface in liquid crystal turbulence, which show that indeed the scaling of the limiting flow of such an interface looks like this distribution. Okay, so I think I have still two more motivation and two connection of random matrices. So random matrices have been also used more recently to understand the critical points of random functions. Okay, so for instance, in deep learning, you have a random function that you want to optimize. So the randomness comes from, for instance, from the synapse that you want to model. And you want to build, for instance, a gradient descent to go to the minimizer of this function. And for that, one of the ways could be to understand the landscape of its critical points. And to understand that, well, you have to understand where the gradient of your function is vanishing, but also the Hessian. For instance, if you want to compute the volume of critical point, it will be given by Craig-Cross formula, which basically depends on the Hessian of your function. And again, so if you have the Hessian of a random function, it will be a random matrix. Okay, so this type of question are also related with question on random matrices. And so the last, I mean, there are again other type of application of random matrices, but this will be the last one I will talk about. So if you look at random graphs, the adjacency matrix of a random graph, which is just a matrix where you put 0 when you have no edge or 1 if you have an edge, will be a random matrix. Okay, and the spectrum of the adjacency matrix of the random graph is also important to understand better its geometry. And so there are many questions which are of this kind to understand the adjacency matrix of a random graph. And recently, there have been a lot of interest in this type of question, for instance, which is called community detection, which are quite popular. And so the idea is that you have, for instance, two communities, and you imagine that in each community, you have some probability that people are going to have an edge, well, vertices of an edge in between each other. Okay, so that's a blue. and another probability to have a relation with the other community. Okay, and then the question that you would like to answer is, being given the graph, how can you recover each communities? Okay, and of course, so if you have if the two communities don't talk to each other, it will be easy because you have just two disconnected graphs. So it's easy to find the communities. But of course, the stronger the interaction between the two communities here, the more difficult it may be to recover the communities. And so there have been quite a lot of study of random matrices, because this type of question can be seen to be related with the eigenvalues and eigenvectors of the matrices. That has been studied recently. Okay, so that's a kind of array of how large random matrices appear in many different settings. And now what I would like to do is to tell you about some results that have been going on what I will consider the Bernoulli random matrices. So because it's a simple example of matrices where we can understand maybe a bit better what is happening. Okay, so what is a Bernoulli random matrix? So it's just an n by n matrix with entries which are 0 or 1 with probability p, 1. Okay, and I will assume that they are independent except for the symmetric constraint. I will just keep the hypothesis during all the rest of the talk that my matrix is symmetric. And now I would like to tell you what we can say about the spectrum of these random matrices, answering quite a few questions that were asked before by the applications. Okay, so one of the interests of this particular example of matrices is that it's related with the adjacency matrix of a random graph, in fact, the R'-Renyi graph. Okay, the R'-Renyi graph is a graph with n vertices, where you draw an edge between two vertices with probability p, independently. Okay, and so if you look at the adjacency matrix of this graph, clearly it's one of these Bernoulli matrices. Okay, and so the R'-Renyi graph has been studied for quite some time, since the 60s, and it's known that there are different properties depending on this probability p of having an edge, and it depends mainly on n times p. Okay, so n times p, if you think about it, it's the average degree of one vertex, because one vertex can draw an edge between other vertices with probability p, and it has about n neighbors. Okay, so if this average degree is smaller than 1, the graph will have no connected component of size again. Okay, if it goes to some constant c, and this is quite what you would expect, I mean, you have a chance of less than one edge between anybody. If the average degrees of order c, then it will have a unique giant component, but still a lot of small components. And if np is now greater than the log of n, then the graph will be almost surely connected. And now what I want to discuss is the property of the spectrum of the Bernoulli matrix, depending on this different phase. So first, what I will do first is to recenter. Well, this is just I recenter the entries by their expectation. This is not really important because this matrix of recentering has just a rank 1, so it doesn't change much the spectrum because the eigenvalues are going to be interlaced. And I renormalize it so that the eigenvalues are more or less of order 1. Okay. And so what we'll discuss is that depending on the average degree Pn, so if it goes to infinity faster than the log of n, then we expect the spectrum of the matrix to be nicely distributed with a continuous density at the limit when n goes to infinity. And in fact, what we will see is that the properties of the spectrum going to be very close to the same matrix if I would have taken a Gaussian matrix. Okay, so this is what we call the Gaussian matrix universality class. And if Pn is now of order C, a constant, then what we see here is that so this will be of order 1, and most of the entries of this matrix will be 0, and a few will be of order 1. And what we will see that the properties of such a matrix are very different from the Gaussian one, what we call AV tails matrices. And there is always a question on when do you go from one type of property, one universality class from the other. Okay, so I will discuss this first the limiting spectrum, then the fluctuation, and then the rare inputs. So the first result that I want to show you, mathematical result, is the limiting distribution of the eigenvalues. Okay, so you look at your eigenvalues, which are real, and you look at the number of eigenvalues which fall in a given interval, AB. A and B are fixed. And what was proven is that when the dimension goes to infinity, almost surely, you have a limiting distribution for the spectrum, and it depends on C. So namely, if C is infinite, what you get is a semicircle law, which is what we get also if you have Gaussian entries. But if C is finite, the distribution looks quite different. And in fact, it can be seen that it has dense atoms. In fact, Justin Salès proves that there are atoms at all totally real algebraic integers. What does it mean? It means there are roots of polynomials with integer coefficients. In the harmonic, so the first term is 1, and all the coefficients are integers. And you can see that the eigenvalues should satisfy such a property, okay, because they should be the zeros of the characteristic polynomial, and because your matrix have integer values, and if you forget about the renormalization, then you get that any the eigenvalues should be totally real algebraic integers. But what Justin Salès proved was stronger, was that in fact any of this was an eigenvalue with an atom. Okay, but it's more than that because you have also a continuous graph as soon as C is greater than 1. So that was this shows that there is a transition related to the fact that the average degree is finite or not at the level of the eigenvalue. And so how can you see that you have creation of atom when C is small? Well, the point is that when C is small, at least maybe smaller than 1, but finite, you will have many graphs which are finite, for instance. So for instance, you have many graphs which are just two vertices with one edge. And if you look at your matrix, what does it mean? It means that you will have one small matrix, which is 2 by 2, with 2 zeros on the diagonal and 1 out of the diagonal. And if you look at the eigenvalues of this matrix, it will be -1 and +1. You see the atom. The point is that such small graph will appear a lot of times. Okay, so maybe just a short slide, one proof. It's a tentative proof, but I like to give it because it shows what people are doing in large random matrices. Basically, it's probability and linear algebra, which is something that you would expect from a random matrix. So how do we prove this kind of theorem? Well, an idea is to look at the resultant, because the resultant has nice properties in the linear algebra. And also, if we see this as a function of the eigenvalues, it's the Cauchy-Stiglitz form of the empirical measure. So from its studies, you can somehow recover the profile of the eigenvalues if you have this kind of quantity for all complex numbers. Okay. And how are we going to compute this limit? What is called the Schur complement formula, which gives us the inverse of the the resultant of the diagonal. And in terms of the scalar product of the minor, where you have expanding with respect to one line and column, scalars the vector xi. So what is nice with this show complement formula is that we assume that we have independent rows. So this vector xi is going to be independent from the matrix, this matrix, where you have suppressed your vector. And from that, you can use classical probability theorem, which will show that this quantity, in fact, concentrate on the diagonal. So you can suppress the off-diagonal terms. And when you look at this term, well, you have just a sum of independent variables, conditionally to that, which are just constant. And so you can use the law of large number. Okay, so if you can use the law of large number, this is when Pn goes to infinity. This means that this quantity self-averages with respect to your entries, and therefore it's almost like the trace of the resolvent again. And from this, you get a formula for Gn. So if you plug it back in your show complement formula, what you get is just a closed equation for the Stiglitz transform that you can solve, and you find that this is the Stiglitz transform of the Cauchy, of the semicircle. If Pn is not going to infinity, so it's very small here, but I can just tell you that here this means that somehow this term will be 0 most of the time, and sometimes it will be 1. So you are just picking randomly some entries on the diagonals, and this term will stay random. So you see that somehow here this term will stay random, and the entries of the resolvent of the diagonal will not be deterministic. And then it's more complicated to compute what is going on when the size goes to infinity, but we can still do that. And we get a different limit law that we can characterize and get this profile I showed you before. Okay, this is finished for the talk. So let me now comment on what else we know and what on the limiting behavior. So if we look at the largest eigenvalue, and this is one of the important quantities in the application too. What we see that there is also a transition, so which is not this time when Pn goes to infinity, but when Pn goes to infinity faster than log n or not. So remember that when Pn is larger than log n 1 plus epsilon, this means that you have a unique connected component, and this is somehow this regime. And in this case, what was shown was that the largest eigenvalue, it sticks to the bulk. Okay. And when Pn over log n goes to 0, then actually the largest eigenvalue goes to infinity, like log n over log n. And if Pn is of order C log n, so this was exactly this transition when C is of order 1, but this time you have a transition at some other value. Then the largest eigenvalue will go away from the bulk. And in fact, you have a clear mechanism which is used to create a large eigenvalue, which is to have vertices with high degree. Okay? And what you can see that when you have this type of average degree, then you can create large value by just having vertices of high degree. Okay, so just to conclude about this result about the asymptotic behavior of the eigenvalue, we can recover somehow the two transitions that we had on the graph. Either we had a Pn which was finite, and then we had a huge connected component, but still lots of small components, and this creates atoms in the asymptotic law. When Pn is going to infinity, you have the bulk is given by the semicircle law, like the Gaussian. But in fact, there is still a transition on the largest eigenvalue, which is related also to the fact whether you have a unique connected component or not. Okay, so that's somehow how you can relate the behavior of the spectrum and the properties of the graph. So now, of course, we are probabilists and we have a lot of other questions that we would like to understand. And the first is fluctuations. Okay, so we have the limit law. Now, what is the typical error that we are going to do when we assume that we are giving by this limit law? And And so the first thing that you can do to understand the error, so this is a tool which has been developed quite a lot in probability since the 2000, more or less. So this is called concentration of measure, and this was called in physics self-averaging. And what concentration of measure tells you is that if you are looking at a random variable, which is a smooth function of independent random variable, then actually it will not be very random. So that's kind of something difficult to grasp at first sight, but this is really what was proven first in the work of Millman, that the volume of the equator has a very small mass, very big mass in the sphere, but here, if you look at this Bernoulli variable, Talleyrand tells you that if you take a smooth function in independent Bernoulli variable, it will be at a distance of its medium, which depends on the Lipschitz constant. And so if you apply this to a function of the empirical measure of the eigenvalues, you can see that this is a smooth function of the entries of the matrix, and you can then control the distance of the mean, the empirical mean to its median by this kind of term. Similarly, for each eigenvalue is going to be a smooth function of the Bernoulli entries, and from there you can see how far it's going to be from its median. So what is nice also with concentration of measure is that this result which hold at any given dimension. It's not only asymptotic, but it's not always sharp. And it gives you some bound, but maybe the bound is far from sharp and it does not give you the asymptotic flow. So now you want to understand things in more detail. And so the first thing that was done was to understand the fluctuation of the empirical measure of the eigenvalues. So if you look at, again, the empirical measure of the eigenvalue, you subtract its expectation, then what is shown is that this object, so without renormalizing a priori by the dimension, is going to converge. So if P is of order 1, you have very small fluctuations. So these are the same fluctuation as for Gaussian matrices. And if P is of order C over N, so this the fluctuation will be as for the usual central limit theorem that you have to renormalize by 1 over square root of N. So you see that the randomness of the empirical measure really, again, depends on this parameter P, and this is really related again with this randomness that we saw appearing when we looked at the Stieltjes transfer. Now, what people have been trying to do quite a lot was to understand more precisely what happened at the local level. Okay, so we have now we understand well the fluctuation of the empirical measure, but we would like to have much finer details. So what is the fluctuation of the largest eigenvalue? Or what is the fluctuation of the distance between two eigenvalues? So this was kind of motivated by, for instance, by the work of Wigner. And so this is a very difficult question because, again, what I didn't say at the beginning, but the difficulty in this topic is that in general, you don't have a nice current flow of the eigenvalues. Okay? And therefore, it's quite difficult to compute things directly. So the point is that when the entries are Gaussian, you have a joint flow for the eigenvalues, which is not super simple, but which is not very difficult to analyze. And this is due to the fact that if you have Gaussian entries, your matrix has more symmetries. So in particular, you can check that the law of your matrix is invariant if you multiply it, if you conjugate it by orthogonal matrices. So it's just because you have Gaussian entries, and the sum of Gaussian is still a Gaussian, so you just have to check that the covariance of the right one. And because of that, you can see many properties for the Gaussian matrices. You can see that if you look at the eigenvectors, so the eigenvectors will be uniformly distributed on the sphere because they have to be invariant by this conjugation by orthogonal matrices. And this shows in particular that they have to be what we call delocalized. Okay, because the uniform law on the sphere, each entry is going to be of order 1 over square root of n. And you can look now at this fluctuation of the largest eigenvalue. And this is a much more complicated computation, but this was done by Tracy and Whedon in the 90s. And what they show is that the fluctuation of the eigenvalue, of the largest eigenvalue, is not at all like the Gaussian. It's on a different scaling than the Gaussian. It's n to the 2/3. And the limit law is what is called now the Tracy-Whedon law, is very different from the Gaussian. So here are a few plots. And also you can compute what happens locally. So in fact, you can even compute the limit law for the difference between two eigenvalues. It's going to be of order 1/n, okay, because all the eigenvalues are constrained to go for the 1 at the limit. And then you can pinpoint exactly the distribution of the difference of the eigenvalue. But this is really due to the fact that for Gaussian matrices, you have an explicit joint law for the eigenvalue. So what can you do in general? So this was a very long story. But for this example, so it was kind of shown. It was shown that if the average degree goes to infinity fast enough, then the local fluctuation of the spectrum will be the same as for the Gaussian one. So that was really by comparison. It was not something that could be computed directly. It was really thanks to this integrable model of the Gaussian matrices. And by comparison, that it could be shown that the local fluctuation of the spectrum and also the delocalization of the eigenvectors was the same as in the Gaussian case. Okay, so that's nice. And but what happens, if Pn is a further one? So things are much more independent. So if Pn is not too big, then what can be seen is that the largest eigenvalues are going to be somehow independent. And so they're going to be distributed like a Poisson process. Okay, so that's kind of what is expected. And they're going eventually to be far away from the bulk, so it's not so difficult to guess. But what happens in the bulk, actually, it's still for the fluctuation. So if you look at two eigenvalues of your matrix with Bernoulli entries, when Pn is of order C, we don't know what is going to be the limiting gap. What is, if you take lambda I plus 1 minus lambda I, for any I you multiply by n, we don't know at this point what is going to be the limiting distribution, because again, it's not something that is in the domain of universality of the Gaussian matrices. And we have, for the time being, no idea how to compute that. There were advances for easier models of heavy matrices, which are called alpha stable matrices, where the entries are going to have a tail which is polynomial. Okay, so in this case, the idea again is that your matrix is going to be a matrix with lots of zeros and a few one on each line and column. And you can study the spectrum, and it's easier than the Bernoulli case. And what could be proven in this case is that there is a phase which is like the Gaussian fluctuation. So and actually depends. So if alpha is greater than 1, here you have like the Gaussian behavior. But if alpha is smaller than 1, what happens is that you will have a transition, depending if you look at the eigenvalue close to a big enough number or a large enough number, and you have a transition from a Gaussian universality class to a more localized behavior. And here what is shown is just this gray and this yellow. So there is still a lot of work to be done to understand this distribution in the bulk. Okay.
Sorry, but the black line is known. The black line is known.
Okay, so the black line now is known. Actually, this was there was some. So the black line is known for the limit. So if there is a black line, it is known. So namely, what was proven is that at the limit, there should be a transition. The transition should be described by some equation. So this was proven, this was shown heuristically by Tarquini, Viroli, and Tarzian. And recently there was this big paper by Agarwal, Bardella, and Lopato, who showed that indeed the transition is governed by this equation and the uniqueness of solution and so on, but the fact that this is really alive. But it was not shown yet that the random matrix itself, I mean, it's work which is done in the limit, not yet on the convergence level of the random matrices. But this was shown that there is a localized phase here and a delocalized phase, but much below this line. So the transition is so there is a characterization of the black line, but still it's not that complicated. And again, nothing for the Bernoulli case. Another question? Okay, so I had another section on rare events, but I'm not sure how much time do I have. 5 minutes. 5 minutes. Because I'm supposed to take again to talk again about rare events. Okay, let me just have a quick overview about rare events. So I understood that people like it here, so I was asked to talk about it tomorrow. I imagine it's because you asked like. So what are rare events on large radiation? It's when you ask a different type of question, which is what is the probability that the spectrum has a completely different behavior than what is supposed to have typically. So for instance, what is the probability that the empirical measure of the eigenvalue is not distributed like the semicircle law, but like this? And the reason why people are interested is, well, sometimes it's nice to know this probability, but they're going to go to zero very quickly. But also it's nice because sometimes you have the law of your entries is not going to be independent, but it's going to be some function of the empirical measure. And then it's very important to be able to estimate this type of thing. Okay, so again, the point is that in the Gaussian case, so here I wrote it, but you have an explicit joint law of the eigenvalue for the Gaussian case, and then deriving large radiation is kind of easy because you just look at your density and you can work on it directly. Okay, I'm not going to go into detail, but that's history. When basically when you're in the sparse case, when Pn is now small, there is a completely different strategy which can be adopted to find large deviation, which is to find why you have large deviation. You know, how to create that and to show that somehow you have some events which will be followed by the matrix if it wants to create a large event. So here, for instance, I think that to create a large eigenvalue, you want to create a vertex with high degree. So you have to show that this is how the most probable event that you want to do to create a large deviation. So it's some work, but the strategy to prove large deviation is kind of more combinatorial in nature. If you have sub-Gaussian tails, well, that's a problem again, that you have a transition. So if P is equal to 1/2, so you have the most symmetric of these Bernoulli matrices, you can show that the large deviation will be the same as for Gaussian. But otherwise, if P is different from 1/2, you have a transition again between large deviation, which will follow kind of the Gaussian case. So you have a rate function which is like in the Gaussian case. And after this transition, you have a different rate function which will depend more on localization phenomena. So you have a transition in your in the large deviation from delocalized eigenvectors and Gaussian rate function and more localized eigenvectors and a different new rate function. Yes, what I like also to point out is another series of questions, which is kind of nice, and it's not really large deviation, but you're asking yourself the question, so it's a very popular question these days. So you would like to understand what is the probability that your matrix is singular. So this means the determinant equal to 0. You know, in large deviation, you would look at something small, here you want really the probability that the determinant is 0. And so this question is still open, I think, in the case where the matrix is symmetric. But if the matrix has all independent entries, this was solved by Tikhomirov. And what they showed is that the probability that your matrix is singular is going to be the probability to have one line to be 0. So that's, again, kind of the thing that you would like to do is to find out what is the thing that the matrix has to do to get to make this deviation. And maybe the last thing I wanted to point out is another type of question about large deviation, which was due to Chatterjee and Varadhan. So here they asked for a different type of question, which was to look at the number of triangles that the graph wants to make. So this is just the number of triangles is given by the trace of Bn to the 3. Okay, you can just think about it, but you just make this sum of 3 entries, and because Bn is 0 or 1, depending whether you have an edge or not, this counts the number of triangles. And so it's not, and what you can see that the expectation of so now is much bigger, it's of order n cubed. And what Chatterjee and Varadhan showed was that there is also large deviation principle for this kind of thing. But again, this is a different kind of regime of than the one for the empirical measure of the eigenvalues. Okay, so let me conclude. So I was a bit fast on the large deviation, but tomorrow I will talk again about that. So if you want to hear more, with more time, I will be happy to talk with you. So what I try to show is that the large random matrix theory has become quite a mature field in the last 20 or 30 years. I mean, was really like in the 90s, the main results were like this Tracy-Widom result or Voigt-Lescu result, but it was still really in the infancy. I think that now there are really a bunch of progresses in many directions. There are still, of course, many open questions. I think, in particular, when you want to go beyond the Gaussian universality class, there are still a lot of open questions. And also, what is nice with random matrices is that it's evolving with always new questions, so coming from applications. So nowadays, it seems to me, for instance, there is a new trend to consider tensors or new models of random matrices, like kernel matrices, which appear in application. And I think it's really driving the field of this all this impact from outside of new questions and to consider. So thank you very much for your attention.
Okay, I can speak loud. Thank you for the nice talk. Very naive question. So you presented results about Bernoulli random matrices, but are there also results about random matrices where instead of having 2 possible values for every entry, you actually have a finite number of them? And
yes, of course. I mean, it was just I presented the Bernoulli because I think it's nice. We can see the relation with the graph. And you can understand, for instance, why you expect to have delocalized vector. Maybe I didn't insist, or you know, the spectrum, why it starts from atoms. But of course, what people started to study in general was Gaussian. And then to have compactly supported or whatever. I mean, Bernoulli is just kind of nice to talk about because you have this connection with graphs, which makes you maybe better understand the type of result that we have. So that's why, but most of what I said, actually, Bernoulli is one of the hardest maybe to grasp. And also you have questions like, you know, like this type of question, which are only really interesting for the, what I imagine for 0,1 or this one, for instance, you need to have a distribution of the entries which is discrete. Otherwise, it will be just 0 if you have a good.
So for the Gaussian ensemble, really one of the key properties that makes it analyzable is this rotational invariance. In theory of this permutation invariance, I wonder how much of all we've presented is strongly relying on this, or is it a kind of fundamental thing that would depend also on the kind of universality class, or?
Yeah, so it's a good question. So in fact, permutation invariance is much weaker property. But I think so. There was this work of Camille Mal on traffic, and the idea is that if you want to have a theory which is the kind of thing like when you add two matrices, you can get their spectrum, like this kind of framework. You need this invariance by orthogonal conjugation. But if you have only permutation, if you want to sum two matrices for which you know only that you have invariant by permutation, then you don't have a single answer. But so what Camille Mal did was to consider something more complicated than only the spectrum, and this is the traffic. So what he showed was that somehow if you look at these more complicated quantities, which are not like only the trace of the moment of the matrix, but what is called the traffic. Then if you have independence by permutation, you can, from the traffic of the two matrices, get the traffic of the sum of the two. So this is to say that there is kind of analog theory, but then the object that you have to consider are much more complicated than only the spectrum. But indeed, it would be great if permutation would be enough to get the same type of property, but it's in fact a quite.
So if you got the condition of symmetry in the Bernoulli matrix, what is known?
Quite a lot actually. The point is that the problem with on the matrices is that if you start talking with non-symmetry, then you have to, in general, people talk, or you have two types of questions. You can ask yourself about the covariance matrix. So you look at your matrix times its transpose. So this is kind of the thing that Wishart did. I mean, Wishart didn't really look at symmetric matrices. He looked at arrays of vectors, which were not supposed to be symmetric, but then he looked at the covariance matrix. And then most of what I said follows. Now, if you want to look at the spectrum of, for instance, a square matrix with just independent plenary, then it's more complicated, but there are also results, and it converges to this circular law. Yes. But it's much more complicated to study because the spectrum of these matrices is unstable. And you can see that when you don't have a symmetric matrix, the matrix is non-normal. And usually, if you change a little bit one of its entry, you can change completely the spectrum. So that's a nice exercise to make, but that's fine. And because of that, it's much more complicated to study because when you have symmetric matrices, it's enough to look at the trace of moments of your matrix, and then or the resolvent, and then you get the spectrum. But if you have non-normal matrices, you have to do something much more complicated, which uses this trick of Birko. I forgot the name, but yeah, somehow you need to make sure that somehow you don't have pathologies, that somehow the density of the eigenvalue is going to be sufficiently well distributed. So this requires extra work, which usually is to boils down to estimate small singular values of matrices. So it's complicated.
You didn't touch this field, but is there some recent developments in products of random matrices? So, for instance, the Apple spectrum or rotation numbers,
So I mean, maybe here you take a different route where you want to take an infinite product, but of finite matrices.
Finite large numbers.
You take both going to infinity, the product on the size of the matrix.
Yeah, for instance.
Okay, so I think that there was. I mean, for one thing, so yeah, I'm not sure. I don't know about recent results about that, except Ekman did some nice work.
Yeah,
Because
Wayne also,
Yeah.
Chuck Wayne in
Yeah.
in the 80s, and
And I was thinking, Guionnet.
Rouen also had
Yeah.
some results in that.
No, I mean, there are nice results also because in some of these cases you have joint, explicit joint law of the eigenvalue. So this makes things easier, but I'm not aware of very recent results. This was, I mean, there were quite a lot of activity not so long ago because of this nice joint law of the eigenvalues which were studied. But,
Since the presentation here, there was a lot of connection.
Yeah. I mean, that's the interest in random matrices that you have lots of different types with many different connections.
I had a very person and I was wondering, are there any results on stochastic analysis for random matrices and convergence to like
So,
only on quantitative results for convergence?
so you mean, for instance, if you put Brownian motion in the entries?
Exactly, and then I was doing something like a qualitative convergence, like the distribution of the spectrum, something more like some norms quantify the defenders on time and decide what the methods.
I mean, there was quite a lot of study of dynamics, for namely when in your random matrix you put some Brownian motion. Also because this type of result I didn't tell you at all how it was shown, but it was by using dynamics. Because what was first shown was that if you take a matrix Xn and you add a small Gaussian matrix, so things were not for the matrix, the Gaussian matrix, then you say, well, I take my matrix, I want to study Xn, and I add the Gaussian ensemble times epsilon. And then it was first shown that you have an explicit joint law, so this was by Johansson, that it showed that in this case you have universality. But then, of course, that's cheating, so people started to say, well, we can let epsilon go to 0. And so there was, and this was really how this kind of universality result was put. So to get very precise estimate on what happens when you add this kind of Brownian motion to the spectrum to show that it's regularized sufficiently or the fluctuations so that it works. So, I mean, there were a lot of work on dynamics of random matrices. Either, you have time for the one, and then you look at the evolution, or you look really at very short time and you show that it's enough to regularize everything. There were also study of the eigenvectors, in this case of the evolution. But I'm not sure that this is exactly the question, the question that you would like to address. I mean, but yeah, so what is nice when you put Brownian motion in the entries of a matrix is that the evolution is going to be very nice for the eigenvalues. And the eigenvalue will follow the Dyson Brownian motion, which are these particles which are Brownian motion conditioned not to intersect. And because of this description, which again does not depend on the eigenvectors, it was kind of possible to study this type of evolution.
Questions and comments? Okay, so if not, let me join and thank Ali for her instructive and impeccable talk. Okay, I will leave and you can ask any questions. Okay, so open our debate.